My fault of the crowd.
They're expected, it's expected much.
Okay, I'm going to, good afternoon. I'm going to kick things off today just because I have a new postdoc I wanted to introduce to the group. This is Rodrigo Pedrosa. And Rodrigo's from Brazil, and he has his PhD from K-State, and also did a short postdoc at K-State before coming here. So Rodrigo will be working on the role of seed transmission and the management of seed transmission in a couple of important cucurbit diseases. So good timing for today's seminar. Here's Rodrigo.
Any other announcements? Our speaker today is Haley Nelson, and Haley is a native of Iowa, a native of Denison, Iowa, where she grew up. And she came to Iowa State for her undergraduate degree in global resource systems and environmental sciences. And even before she graduated, she was working in our lab and continued to work as an hourly and then as a research associate. And then she transferred to being a master's student where she's been for the last 3 years, and this is her exit seminar. So,
great, thank you.
Turn off this one.
Oh, great. Okay, good afternoon, everyone. Thank you for the introduction, Mark. So, my master's research is heavily management-oriented. The subject of my thesis is disease and pest management in organic muskmelon and squash. Producing muskmelon and squash organically in Iowa is extremely challenging. They are subject to some different pest complexes. Bacterial wilt is a major disease on muskmelon. Symptoms of bacterial wilt are severe wilting of the leaves. Those leaves desiccate, and within a couple weeks, the plant collapses and dies. The causal agent of bacterial wilt is a bacterium. It's called Erwinia tricapella, and the spread of that bacterium is dependent on some insect vectors. The striped cucumber beetle is the primary overwintering vector, and then spotted cucumber beetles are also understood to vector this bacteria. In the absence of this bacteria, both of these beetles are still pests on muskmelon that cause significant feeding damage. So striped cucumber beetles ingest the bacteria when they feed on infected seedlings. Those beetles then overwinter in the soil. They emerge in the spring and they seek out cucurbit plants. The bacteria survives in the guts of some of those beetles through the winter. Those beetles, they cause a lot of feeding damage on the cucurbit seedlings, and they're also at the same time excreting their waste, leaving behind their poop, or frass, as entomologists classically call it. And in their frass, that bacteria can be found. When their infected frass touches any of the abundant feeding wounds that they've created, that bacteria then gains access into the xylem of the plants. It's very happy in the xylem, it multiplies and gums up the xylem, it reduces water flow, and that's what gives you the characteristic wilting symptoms. Cucurbit yellow vine decline is also known as CYVD. This is a disease on squash in Iowa. The symptoms of CYVD are yellowing of plants. Seedlings can show wilting symptoms, and plants will just completely collapse. The causal agent of CYVD is also a bacterium. It's called Serratia marcescens. And similarly to Erwinia tricapella, this bacteria also requires an insect vector. And the insect vector is the squash bug, Anassa tristis. And it also will cause significant feeding damage on squash plants, even in the absence of the bacteria. Squash are also subject to some additional pests. Both of those pictures are of squash vine borer. One is the larvae, one is the moth. It's very sad if you have that pest. It will decimate your squash. So managing these crops is extremely difficult in organic agriculture. My work focuses on organic agriculture specifically. And for the rest of my presentation, I will talk to you about some of the current best practices that organic growers have available to them in practice. I'll segue into my field research trials that I did for 3 years, which are funded by USDA NIFA Organic Transitions Program. And then I'll also comment on a teaching case study that I wrote. So for managing those pest complexes I mentioned in Iowa, organic growers depend on a strategy that combines the use of insecticides with low tunnels. Low tunnels are a physical barrier that prevent the pests from feeding on the plants and spreading these diseases. And I'll explain kind of how that system works. In the spring, growers transplant cucurbit seedlings in the soil. Immediately after they plant those seedlings, you cover the seedlings with this row cover fabric. That fabric is suspended above the plants on wire hoops that are staked into the ground. At their maximum height, they're about 1.5 feet above the soil line. They're short, which is also why we call them low tunnels. The row cover fabric is very effective at preventing the pests from feeding on these crops and spreading disease, but they have to be removed after 3 or 4 weeks. And there's a couple different reasons for that. The first reason is that cucurbits are insect pollinated. So to allow the pollinators to have access to this crop, we remove that fabric as soon as female flowers appear. The second reason we remove this fabric is because it traps a lot of heat. You can't leave it on all summer because it will kill those seedlings. So once you remove that row cover fabric after only 3 or 4 weeks in the season, growers depend on organic insecticides to manage those beetles and squash bugs and other pests. The disadvantages of this system are that the organic insecticides some of them are toxic to bees. They don't weather very well, and they're just not very effective. And then the low tunnel have some disadvantages. The benefits of that row cover fabric are limited to a very short period of time at the beginning of a season. And then that fabric is also not very durable. It tears very easily, and a lot of times growers have to replace that fabric annually, which gets expensive. So this brings me to my field research trials. The aim of my field research is to test the performance of modified tunnel systems and compare them with the low tunnel strategies. The modified tunnels that we tested we call mesotunnels, and we used some new materials to create these mesotunnels. We used a different row cover fabric in our mesotunnels. We used a mesh insect netting. It has holes in it, but the holes are small enough to prevent the insect pests from accessing the plants and spreading disease. But because it has holes in it, that allows air exchange and allows us to leave that fabric on plants for the entire season without the risk of overheating plants and killing them. The second modification we made to the tunnel system was to use taller support structures. Instead of the short wire hoops, we used 1-inch diameter galvanized metal conduit pipes. They're 10 foot long. We bent them into a hoop structure. When they're in the soil, they stand at about 3.5 feet tall. We wanted these to be taller, again, so we could leave these on plants the entire season and not restrict the space that plants have to grow over that season. So using these new materials, we created 2 slightly different mesotunnel systems. We have a part season mesotunnel. These mesotunnel strategies, you apply that row cover fabric over the plants in the spring immediately after you transplant your seedlings. But they differ in their pollination strategy. So for pollination in the part season mesotunnel, when female flowers appear on the plants after 3 or 4 weeks, you remove that row cover fabric, you leave that off for a 2-week time period. In that 2-week window where the plants are vulnerable, you scout for your insect pests and apply insecticides if you reach threshold. After that 2-week window, you then recover the plants with that fabric. You leave it on for the rest of the season until harvest. For pollination in the full season mesotunnel, when female flowers appear, again about 3 or 4 weeks into the season, you order bumblebee hives. They're about the size of a shoebox. You put one of those in the end of a tunnel, and you leave that there for a minimum of 3 or 4 weeks. So in the full season mesotunnel, you never fully remove that row cover fabric at any point in the season. It stays on the plants from transplant until harvest. So to give you like a visual diagram of how these systems compare, you can see for the duration of the season from May to August, there's 3 different time points. You have transplant, you have a pollination period, and then you have the time until you harvest the plants. If you look at a non-covered system that doesn't use row covers, you're having to depend on insecticides for the entire season. If you compare the low tunnel system with that, you can see you're getting the benefit of row covers for a short window in that season. And then if you look at both mesotunnel systems, you can see you're either reducing the use of insecticides or completely eliminating their use. So for my field research, we compared both those mesotunnel treatments with the low tunnel system as well as a control that had no row covers. And we tested this on both muskmelon and acorn squash. The response variables that we measured were yield, disease and pest, incidence of disease and pest injury, insecticide applications, and the temperatures underneath the row cover fabrics. So I'm going to explain some of my results that I had on muskmelon first, and then I'll get into acorn squash after that. This graph shows the weight of marketable fruit. That's fruit that a grower could sell in each of these treatments. We're going to do muskmelon first, and you can see we have results for all 3 years. So in 2016, the full season mesotunnel, so that's the blue bar there, resulted in a significantly higher yield than all 3 other treatments. In 2017, both mesotunnel strategies had the highest yield. The low tunnel had about half that yield, and then the non-covered control had significantly lower yields than both mesotunnel treatments. And in 2018, you see the same pattern as 2017. Okay, this graph shows the incidence of disease and pest injury in muskmelon. That includes bacterial wilt, feeding from the insect pests, and just general plant knockdown, because it's very difficult to distinguish between all of the problems that you get on muskmelon. And we have this for 2 years. In 2017, there was no incidence of disease or pest injury in our full season mesotunnels. There was a little more in the part season mesotunnels, and there was significantly more disease and pest injury in the low tunnels compared to the full season mesotunnel, and about the same amount in the non-covered control. In 2018, again, the full season mesotunnels had 0% incidence of disease and pest injury. Part season mesotunnels performed equally well. Low tunnels had some more, and then the non-covered control had significantly more disease and pest injury than both mesotunnel treatments. Okay, and this graph shows the number of insecticide sprays that were required for each treatment. So in 2016, full season mesotunnels required 0 insecticide sprays. The part season mesotunnels required an additional spray. Low tunnels required an extra spray above that, and then the non-covered control require 6 insecticide applications. And in 2017, you see a very similar pattern. In 2018, there was a lot fewer insecticide applications across the board. Okay, so hopefully you're all still with me. Just to kind of summarize, to bring that all together for you, since numbers can get a little boring. We think about yields on muskmelon across these treatments. The mesotunnels produced 2 to 3.5 times the yield of other treatments. There was 0% incidence of disease and pest injury in the full season mesotunnels, and the full season mesotunnels also required 0 insecticide applications. So we also measured the temperatures underneath both of these different row cover fabrics. We put temperature sensors under 3 different mesotunnel treatments, put them out under 3 different low tunnel treatments, and then we also put them out in 3 different non-covered treatments, so that would be the ambient air temperature. We put those sensors in between 2 rows of plants about 6 inches above the ground. And those collected temperature data every hour. So this graph shows the maximum daily temperatures underneath each of those treatments. And that gray line represents the maximum daily temperatures underneath that low tunnel fabric. You can see the temperatures get a lot hotter. Temperatures reached up to almost 160 degrees Fahrenheit, which is a temperature that will certainly kill seedlings, and it frequently does. And then that blue line represents temperatures underneath the mesotunnel, and you can see that the temperatures in the mesotunnels are not much higher than the ambient air temperature. Okay, so now we'll go into some results on acorn squash. And just to remind you, we have some different additional pests on acorn squash. We have the squash bug, and then also the lovely squash vine borer. So this graph shows the weight of marketable fruit. Again, we're focusing on acorn squash now. So in 2016, the full season mesotunnels had the highest yields. Both the part season mesotunnel and the low tunnel had lower yields than the full season mesotunnel, and the non-covered control had significantly lower yields than the full season mesotunnel. In 2017, both mesotunnels performed equally well. The low tunnel had a little less yield than the mesotunnels, and the non-covered control had significantly lower yields than the mesotunnels. And in 2018, the full season mesotunnel outperformed all 3 other treatments. Okay, so this shows the incidence of disease and pest injury in acorn squash. In 2016, both mesotunnels had no incidence of disease or pest injury. The low tunnel had a little more, and then the non-covered control had significantly more disease and pest injury than the mesotunnels. In 2017, the full season mesotunnel had the least amount of disease and pest injury. It did have some. Part season mesotunnel had some more, and then both the low tunnel and the non-covered control had the most disease and pest injury, which was significantly greater than the full season mesotunnels. And in 2018, the full season mesotunnels had significantly less disease and pest injury than all 3 other treatments. And since we're just coming off of a slide talking about disease and pest injury, I thought I'd show you and give you an idea of the injury that we saw in the field. You can see some yellowing and empty patches in there. That non-covered control, there's definitely a lot of plant knockdown in there. And you can see, even in our full season mesotunnels in 2018, you can see some yellowing in there. Okay, so for the number of insecticide sprays that were applied to squash, you can see a lot more insecticides were needed on squash than on muskmelon. That's because we have some more pests that we have to spray different pesticides for. And you see the same trend in all 3 years. The full season mesotunnels required no insecticide applications. You needed some more for the part season mesotunnel, more for the low tunnel, and the most sprays were applied to the non-covered control. So to summarize our findings on squash, for yields, the full season mesotunnels produced the highest yields on squash. Full season mesotunnels had the lowest incidence of disease and pest injury, and they also required 0 insecticide applications. So the second component of my master's work has been to write a teaching case study. This is a peer-reviewed publication. Well, that's what I'm aiming for. I haven't submitted it yet, and it would be published in the Plant Health Instructor on the APS webpage. For my teaching case study, I wrote this for the audience of an undergraduate introductory plant pathology class. And I had teaching objectives, or learning objectives for the students to learn. I focused on kind of adding complexity to the disease triangle, because we also have to think about insect vectors. I took this sort of right out of my master's work, so it's about the bacterial wilt pathosystem on muskmelon. And then it also tried to teach students about the difficulties of organic management of these pests. And so in my case study, I put the students in an imaginary situation that could be real life, and made them sort of act as the growers, so that they have to learn about this pathosystem and propose management strategies, and it forces them to really understand the realities the growers face. And I will be presenting this case study on Thursday in mixed class. And so that's a requirement for, before publishing this case study, that I have to present it. I'll get some feedback from those students, be able to make some changes to this, and then submit it for publishing. And then, so this is actually on the APS website where those case studies can be found in the education unit. Okay, so before I finish my presentation, I would like to acknowledge USDA NEPA's Organic Transitions Program for providing funding for me to do this research. I would also like to thank my wonderful advisor, Mark Gleason. And I have a lot of people to thank. I will do that in person and not pretend like I've won the Academy Awards today. But I do want to acknowledge all the undergraduates and everybody in my lab who has helped with making this project happen every year. It is not an easy project to get underway, and I have had a lot of help to make it happen, and I appreciate that. Thank you to you all. So thank you for being here. I will take questions.
I might have missed that, but so you have like represented two data where one is like incidence of pests and disease onto use like different tunnel types and no cover, and then like number of sprays used in all these.
Yes.
So that data is from all the treatments like where the sprays are applied, for example in no cover. So you have applied all the sprays and you are taking the data. Is that correct?
Yes.
And still like with these sprays the incidence was that higher?
So your question is, so you're saying we applied different insecticide sprays to each of these treatments based on thresholds. They had different amounts of applications.
Exactly.
And then you're noticing that we also had a lot of disease and injury on these treatments, even though that we had these sprays. Yes, that's a really good point. I think that says a lot about the challenges of managing these pests organically. Like it's just, I think you've noticed that insecticide sprays for these pests at least are just, they're not cutting it.
This related to that. It was one insecticide that you used, and appropriate?
So it was a trio of insecticides for squash bug and cucumber beetles. We sprayed a mixture of a kale and clay, a neem oil, and a pyrethroid. And then, oh yes, I'm sorry, pyrethrin.
So that's
the organic.
but
Yeah, exactly.
pyrethroid is
Pyrethroids
not.
would be conventional.
Okay.
Yeah. And then for the squash vine borer, we sprayed BT.
Okay. So perhaps that's totally ineffective, right? You didn't really have an unsprayed control.
Correct. We did not have a control that was not sprayed at all.
So if you thought the insecticide was effective, how does that compare to the cost of getting the bees? I guess those are just disposable hives. They're like temporary hives that you
Yeah.
buy and then you just let the bees die or go.
Yeah, good question. So the question is about the cost of the hives and bees and how that compares against the cost of the insecticides, right?
Yeah.
So the hives cost, the price went up, they cost $120, I think now. They are one-time use at the end of the season. They all buy. So I will say we haven't done an economic analysis yet, but we will be doing that.
But
So
it's
I'm not
kind of
sure.
pricey, because you have to buy
Yeah.
one of those for each row.
Certainly, yeah. And that's, I guess, can I mention Kevis's work? That Kevis is gonna be looking at how far one of those hives will go. My treatments were 30 feet long and 21 feet wide. These hives are intended for greenhouse use and intended to cover a lot larger area, but Kevis's work is gonna see how much area will they cover out in the field. Can we use one hive for 150 feet of row? So.
But that hive, you actually have to leave it in there, because they're gonna come back.
Yes,
That
you
hive
leave that
usually-
hive in there, yeah. Chelsea?
So my question was kind of along the same lines. So I watched a documentary, like everybody does. And there was a documentary about honey, and they were talking about how you can like rent hives out. Would that be a cheaper option than just like getting these disposable hives? Because it's, we've got like this crisis of all the bees dying. Would it be better to like make sure that the bees go back home?
That is a really interesting thought. So I don't know much about how those rental hives would work, but I suspect they wouldn't do so well because they have to be inside that tunnel, right? I have an entomologist sitting in front of you that knows a lot more about hives than I do.
Pollination services, where you rent out beehives to growers, would be higher cost than the bumblebees. It's about
Okay.
$200 per hive to rent them.
Oh, so the bees you're using are bumblebees? They're not
Correct.
honeybees?
Correct.
Okay. And then, let's see. Oh, with the beetles with like the chewing mouth parts, are they able to chew through the mesh at all?
So I can't say that, I never noticed any, I can't say that I saw them chewing through the mesh. No. Yeah, so we did trap in 2016, and beetles are getting underneath that material. So it's not keeping them 100% out, but somehow we have less disease.
We used to actually bury the edges of these funnels, and that's a lot of work, and it means that you'll never get to use that material again. It's hard to get up in the fall. And that was 100%, but now we're just using these, you just can't even see them, but with these rock bags to hold down the material. Like she said, it works pretty well. Probably taking 98% now.
So how much light is obstructed from the mesh and from the other. I would think that that would reduce the photosynthetic capacity somewhat because of the reduced light. Do you see any evidence of that?
Evidence in the form of,
I don't know how
see
you do it.
shade, right?
Do you ever measure underneath there to see how much?
No, we don't measure the light underneath the tunnels.
I think it's true that they would have more light transmission than the low tunnel materials like remake or agribon. That's shadier, but even there, it's only part season, but there's no quality difference in the melons. And the productivity, under this system is pretty high.
Well, I'm thinking in terms of some of like David Gaduri's work where he's looking at how light influences fungi and the fungal reproduction and wondering if, I don't think that the bacterial system is going to influence it, if this mesh could actually be beneficial in keeping some other fungal populations down because it's obstructing just enough light to influence their reproduction cycles.
We actually sprayed a time or two, we being you, actually sprayed a time or two of fungicide inside the mesotunnel. One of the advantages is that you can spray through it, which you can't do with the other material. Is there another question there? Okay.
So when you're using the material, how durable is it compared to the other material? And then as far as using it across years, and then how expensive is it compared to the other material?
Okay, and that is the ultimate catch. Yeah, so the question is about the durability of the mesh insect netting and also the cost of it. So we are going to do an economic analysis. But so with the durability, we were hoping that this would hold for 3 years. What I noticed was that on the muskmelon, the tendrils of the muskmelon would wrap into those holes, and so at the end of the season, when you pull that fabric off, you would get small holes in the netting. So we actually mended those holes every year, which I don't know, I doubt a grower would want to do that. It's definitely time consuming. I would be interested to see if you reused it without those holes, if you reused it without mending those holes, if the beetles would take advantage of that and get in there. So that's definitely a problem with this fabric. As far as the cost of the insect netting, it does cost 3 times as much as the low tunnel fabric. So that is a big drawback of the system. Joey?
Is there a natural enemies ever been identified for these insect pests?
My understanding is that there have been some identified. I think some beetles will act as predators of these. I've heard of bats are also considered a predator of these. I can't think of anything else.
There are parasitoids that may attack, especially the squash bug eggs, but their effectiveness is moderate suppression at best.
Other questions? Oh, thank you.